Okay, so today we're going to talk about what we call post hoc procedures. And so we've been, chapter 11, we've been talking about ANOVA, analysis of variance. And pretty much, here's what's going on here with ANOVA. So remember, ANOVA tells us whether there's a difference between the means or not. Okay? It can tell that. But it doesn't tell you which differences there are. Okay? So, just as a review, the null hypothesis is that all the means are equal. Okay? And the alternative is that they're not all equal. So this alternative is pretty big. If the alternative hypothesis is true, it could be true with just this one being different from the other three. Okay, so these three could still be equal. But if this one's different, then you're in the alternative. Okay, and you're rejecting the hypothesis. Okay. So ANOVA just tells us that, but doesn't tell us which means are different from each other. Okay, now at the beginning of this section, we did the Bonferroni. And that could tell us which ones are different, but it has low power. Okay. You guys remember what it means by what low power means? Remember that? Hey, go.
Sorry.
What?
I got scared when I saw it.
Oh, are you taking a video? Yeah, taking video. Don't want to bump it. Low power means? Somebody want to take a crack at that?
Excuse me?
What is low power? What does power mean? You guys remember? No? Does anybody remember what power is? Power, if the alternative is true, the power is the probability of finding out that it's true. Okay. But here though we're talking about comparing, say, this one with that one, not comparing them all. Okay, so with the Bonferroni, you're comparing them. You're making several comparisons, but there's low power in that. Okay, so if two of those are different from each other, it's hard to pick that up. It's harder to pick that up with the Bonferroni. So the solution is this one right here, the Tukey something. This one, all that is basically is when you run the analysis ANOVA, then you just check a box, and then it will give you that. So, but I'll show you how to interpret it though. Okay, so it's like the Bonferroni, but it has higher power, and it compares every possible pair, and it can use the same process to construct many confidence intervals. Okay, that's what it is. It constructs confidence intervals for every single pair, and that's what you look at. And also, it gives you p-values for every single pair as well. Okay, so here's the steps for using it. First, you have to check the conditions for running ANOVA. Remember, so like for example, you need to have either normal distribution for your samples, independent samples. At least 25 or normal, and the standard deviations not too far apart from each other. Okay, then after you check the conditions, you run ANOVA using a computer to find the p-value. Okay, now if the p-value is more than your level of significance, that means you're not going to reject the null hypothesis. And what that also means is that you're going to just stop right there. Okay, so if you don't reject this, if the means are all equal, then you're not going to run any further analysis because it already says that you don't have that much evidence to say that the means are different, that they're not all equal. Okay. So in this case, you don't do the Tukey thing. You don't do it. Okay. But if the p-value is less than alpha, then that means that not all the means are the same. Then you use this one to figure out which ones are different. And it'll give you confidence interval for all the differences. Okay, so let's go ahead and do this one. We'll have Ethan here. Ethan's not here. How about Felicia? Felicia, can you read that for us?
It's interested in whether the season is a factor is in quantum of money couples spend at the carnival.
Okay, thank you. So we're looking about whether season is a factor. Okay, so Princess, what are the different seasons of the year?
Winter, spring, summer, fall.
Winter, spring, summer, and fall, right? Okay. So now, what do you think is going to happen here? People spending money at the carnival. Which season do you think is going to be spending the most money?
Summer.
Summer, okay. And which do you think might be the least?
Winter.
Okay, so that's a good idea to think about what the problem entails. Okay, so if we set up a null hypothesis, what is the null hypothesis going to be for this problem? Okay, we'll ask show.
All the means the same.
Yeah, they're all the same, yes. Okay, so the null hypothesis will be that they're all the same. Good, just like that. And then for the alternative, what would the alternative be? We'll stick with show.
At least one of them are different.
At least one is different. Or the way they say it is they're not all the same for all seasons. Okay, so in this case, supposedly they collect the receipts from randomly selected couples from each of the seasons. And maybe they just made up the data, but we'll just, we'll go along with it. Okay, so here's what an analysis of variance came up with. Okay. I don't think. Does this show up when you do analysis of variance? Maybe not. Okay, but this does right here. This is his term table, and the important thing is that the p-value is less than is really small, which means you reject the null hypothesis and accept the alternative. Okay, so that means that they're not all. Well, that means there's statistically significant evidence to conclude that they're not all the same. Okay? And they're just noting a couple of things, that the sample sizes are all greater than 25, right here, 26, 27, 28. Also that the standard errors, the largest one, 0.33, is not more than double the smallest one. Okay, so if you take the smallest one and double that, you're larger than the largest one. Okay, so that means that because we rejected the null hypothesis with a small p-value, that means that we can both proceed with the Tukey. And basically what that is you just check a box when you do the ANOVA. I'll show you how to do that on StatCrunch in a little while. Okay, but here I'm just going to focus on interpreting the results. Okay, so this is a little bit confusing because it says winter subtracted from. Okay, so let's write that down. Okay, so winter subtracted from, and put the first one down, spring. Okay, winter subtracted from spring. Okay, so if you wanted to write an expression for that, what would it be? It'd be what minus what? Yeah, that would be spring minus winter. Okay. So now, in this case, we have a lower, this is the confidence interval. The lower limit is this one, and the upper limit is this one. So the confidence interval is about 5.78 to 21.40, approximately. And that's our confidence interval for spring minus winter. Okay, so now if it's spring minus winter, which one is bigger? If that's the confidence interval, we'll go with George.
Spring.
Spring is bigger because, how can you tell from the confidence interval? Because what? Because this interval, so if this is 5.78 and this is 21.40, and all the numbers in here are positive, right?
Yeah.
And where's 0?
To the left.
0's to the left. 0's over here. Okay? So any of these numbers in here, you're going to have spring minus winter being positive. That means spring is larger than winter. The spring values for anything in the confidence interval. So that means that it's significantly larger. Spring is significantly larger than winter. In fact, when you have, if the confidence intervals are all positive, meaning both endpoints are positive, meaning the lower and upper are both positive, that means that the mean receipts for this one are lower than these. Okay, when it's positive. Yeah.
Like, is there a standard when you can say this, like spring is significantly larger? Because there's a question was like, is it significantly higher? Like, what makes it significantly higher? Is there a certain number?
Yeah.
Above? What is it?
No. It's just whether both values are positive. Okay, so you could either have both values being positive, or you could have a 0 in the middle. 0. Confidence interval contains 0, which means one of your values is negative, another is positive. Okay? So if the confidence interval contains 0, then they're not significantly different. Okay? That answer your question? Okay, good. And so that's the other case. If one is negative, another one's positive, then they're not significantly different from each other. Okay? And then the third case, because if you have your confidence interval contains 0, okay, so that means that minus that could be 0. Okay, in this case it would be summer minus spring or fall minus spring. Okay, and then the third case is where both the values are negative. Okay, so here we have, let's see here. I see Daisy. What is this last one? This is okay, summer subtracted from fall. What would that be? It would be what minus what?
Should be the negative.
Yeah, it's which one here? Fall or summer?
Fall.
Okay, yeah, it's fall minus summer. That's the last one. So that's when you say summer subtracted from fall, that is fall minus summer. And they're both negative. So that's negative 16.95 and then negative 1.61. Okay, there's your confidence interval. Now where's 0 in relation to this? To the right. So 0 is over here. It's outside the confidence interval. So that means that they are significantly different. Okay? Significant. So 0 not being in the confidence interval means significantly different. In this case, because this is negative, that means that summer is significantly larger than fall. Okay? Summer is significantly larger than fall. This case, since it's positive, that means this one is significantly larger than that one. Okay, also let me point one thing out here right now, and that is, okay, this is a confidence interval for fall minus summer, or the mean for fall. These are really dealing with the means here. Okay, really dealing with the means. If you wanted instead of and so we got fall minus summer. If instead you wanted summer minus fall, and instead if you wanted the confidence interval for that one, what do you think it would be? Okay, so for fall minus winter, our confidence interval is from negative 16.95 to negative 1.61. Okay, so if it's this one though, from what to what? Anyone want to take a guess at that? Okay, out of summer and fall, we determined that summer is significantly larger than fall, so that's got to be two positive numbers. Okay, so you got to be both positive. But what numbers would we choose? Okay. Then maybe this is a bit confusing, but I'll tell you right now, and hopefully some people will remember. Okay, so this goes from negative 16.95 to negative 1.61. So what you want to do is you want to make those both positive and reverse them. So you're going to go from 1.65 to 16.95. Wait, 1.61. Oops. 1.61. So positive 1.61 to positive 16.95. So reverse the numbers and then you. It's kind of like this. If you have, think of x as being your a value in the confidence interval, okay? And let's say you've got, so originally we had negative 1.61 here, and we had a negative 16.95. Okay, so now if you multiply everything by negative 1, then negative x, you have to flip the directions. Okay, you flip the directions, and so, but then this kind of goes the wrong way. So I'm going to rearrange it like this. Okay, so that's just a little bit of an explanation. So basically, whether or not they are significant is whether or not 0 falls in the confidence interval. If 0 is in the confidence interval, then they're not significantly different. Okay, now, so we found. So here's what you do to visualize the confidence interval. Here's what the textbook wants you to do. Okay, so you order them from smallest to largest. Okay, from the smallest mean to the largest mean. And so this is the smallest, winter, and then the second smallest is fall. So winter, then fall, then spring and summer. Okay, so you do that. And then you look for the confidence intervals that have 0, and that spring and summer does. And so because spring and summer might be equal, then you put a line right there over spring and summer. And then also, what was the other one? Spring and fall. Spring and fall also, so you put a line there. Okay, so you put lines under the ones that could possibly be equal. So that's how they want you to.
Does it mean all the 3 seasons made equal?
You know, that's interesting because it found significant differences between fall and summer, right? So, but what you're saying is these two could be equal and these could be equal, right? But if they're all 3 equal, then that means the fall and summer are equal too, right? So that's yeah.
Where do you base it
But-
from? The equality?
Whether they're equal or not, whether 0's in the confidence interval,
Oh, it's a 0.
okay? Whether 0's in the confidence interval. And it's only for these two. Okay, so you have a good point, Daisy, but you know that's not how it works. Because fall was significantly different than summer. So, so even though fall and spring are close to each other, and spring and summer are close enough to each other, that's not significant. I suppose that one of these two is probably not going to be the case then, right? Either that's not equal to that, or that's not equal to that. If fall is not equal to summer, that's one of those two's got to be the case. But don't know which one though. Okay, so that's basically how you do it. Now, let me just go through this other example here: GPA by race. Erase a factor in GPA. You just said there's the null hypothesis, and then the alternative is that they're not all the same, and some of the conditions are met. And of course, if you do some kind of study on like this, when this kind of sensitive issue, then of course you're going to end up with a high p-value because everybody's the same. All the races are equal in every way, right? So if you try to say that they're not, then you're going to get in trouble. But statistics, fortunately, shows you that you've got a p-value of 0.924. Okay, so what does the p-value of 0.924 mean that you do now? We will ask, hey Jordan, what does the p-value of 0.924 mean?
It's further away from one.
Yeah? What do you mean? Further away from 1. Okay, so what does it mean in terms? Yes, further away from 0, so which means that you, what is that? Do you reject the null hypothesis or fail to reject the null hypothesis?
Fail to reject.
Okay, good. So you fail to, this means fail to reject the null hypothesis. And then what's your conclusion? In terms of, so you fail to reject this, right?
Mm-hmm.
So you conclude what? That there's not significant evidence that they're not all equal.
Yeah.
Okay. So basically you're saying we don't have significant evidence that that there's any differences between means, right? So because that's the case, then simply do not proceed with the other analysis. Just don't do it. Because you don't have evidence, you don't have significant evidence that the means are different. So you don't proceed with the Tukey HSD. Okay? So now let's go and take a look at some exercises from 11.4. And I know George had a question on number 4, so we will start with that one right away. We'll do that one first. Let me see here. Okay, so we're going to go ahead and do this one here. Let me see if I can make this bigger. In the meantime, let's see. Taylor, can you? Oh, Taylor's not stepped out. Cheng Shun Mao. Can you read that for us? Is that too small? I'm trying to make it bigger. There we go.
Data were obtained from random samples of workers entering the hardware store who were asked how many hours of work they performed in the previous week. The workers were electricians, plumbers, and construction workers.
Okay. So there's 3 kinds of workers, right? Electricians, plumbers, and construction workers. Now, apparently right here it says decide whether a p-value of 0.006 for ANOVA suggests that post-hoc test should be done. So, what do you think? We'll go with Max.
Is it
So you got a p-value of
should be done?
0.006. So that's pretty small. That means there's significant differences. So,
Should be done.
so yeah, it should be done. Based on that alone, okay? Of course, we should probably just calculate this stuff on our own.
Do you compare it with the 0.0 comment?
Yeah, 0.05. Okay, so 0.006 is less than 0.05, which is the standard, which is like if it doesn't say anything, and that's what you use. And so 0.006 is less than 0.05. So we reject the hypothesis. That means we do. There are some differences between at least. They're not all the same. That means they're not all the same. And so we do proceed with the Tukey thing. Okay? So now it says use an overall level of significance of 0.05. And then in the parentheses have all these notes here, but don't follow that because we do have access to the StatCrunch stuff. Okay, so you're going to report the confidence interval for construction workers to electricians. Okay, so once again, you go here and open this up, and here's all your data. And then we're going to go here and open it with StatCrunch. Okay, what I'm going to do, I'm going to move things around a little bit. Okay, so once again, if you just open StatCrunch, you can input these numbers here and put these tiles across there if you needed to. Okay, so we're going to run. So we're supposed to find confidence intervals, but what you need to do first is run ANOVA on this. So let's see, Lauren, remember how to run ANOVA?
So stat, ANOVA, and then
Yeah, so stat, ANOVA, and one way. Okay, good.
select them all,
Select all those.
and then you go down and click the compute Tukey HSD, and then
Yeah, so good. So this is basically what's different about this section is you're going to click this button right here, and then you're going to go to compute. And it gives you a bit more than what was shown on the PowerPoints actually. It gives you more information. But anyways, I guess it does give you the column statistics right here. And you can compare the standard deviations. The largest one is 3.4. The smallest one is 2.5 something. If you double that, that's like 5, which is still less, which is greater than 3.4. So we're good on the standard deviations. The 15 is a little bit low, but I guess we're just going to assume that it's okay though. And the p-value is 0.0062, which is what they told us. So good for them. So now, you want construction minus electrician. So here we have electrician subtracted from construction. They actually give you two additional values, the difference and the p-value. Okay. Two additional values that were not given in the PowerPoint. Okay. So, anyways, Stephen?
Yeah.
What would be the confidence interval from construction minus electrician? Or, so here we have electrician subtracted from construction.
So then the difference.
Yeah, so, okay, where it says electrician subtracted from construction. Okay, that would be what minus what? It says electrician subtracted from construction. That's what minus what?
So is it? I'm not sure. Is it the 11 and the 12 that's there on the difference tab or no?
It would be, wait, electrician subtracted from construction. That means that this will be construction minus electrician. Okay, so it's just a little bit of hard English right there. Okay, which is what we want, right? We want construction minus electrician. Okay, and so then what? Did you want to guess what the confidence interval was supposed to be? The limits for the confidence interval. So you want to look at this line right here, and for the lower limit, which number are you going to choose?
2.6.
Yeah, 2.6 something. And it says, darn it. Two decimal places, so 2 point what?
2.61.
0.61, and then the upper limit would be
22.32.
okay. Nice work. Yay. Okay, now for this one, we're going to go with David Rukami. So can the null hypothesis of no difference be rejected for this pair? Okay, so the confidence interval goes from 2. Okay, so if we put a number on that, it's 2.61 up to 22. Wait, 22.32, right? Yeah. Incidentally, this 12.47 is exactly in the middle. That's exactly in the middle. So basically, it's it's actually 12.466, bunch of sixes, plus or minus the error. That's how the confidence interval works. And the error puts us, the plus is here, the minus is there. Okay. So now, where's 0 on this scale? Okay, so 0 is over here. That means are these significantly different? Remember, if 0's in the interval, then they're not significant. They're not significantly different. But if 0's outside the interval, then they are significantly different. Okay, so that means, the null hypothesis means that they are not significantly different. They're the same. The null hypothesis means that they're the same. But this is saying they're significantly different. So the null hypothesis can be rejected in this case. So you're going to go with it can be rejected. Okay? Yeah?
In this case, when the p-values are both below the level of significance, can you not just say that because those p-values are below that you can reject the null hypothesis?
Yes. So you could also look at the p-values. This is 0.01.
Right.
Okay? So the p-value is 0.0102, which is less than 0.05. So reject. It's not. So yes, that's a good point. And so, yeah, and then that one is 0.02, so you can reject that too, and that's 0.953, so you failed to reject that one. Okay, so the next one is, I'll just keep going. Joseph Young. So the next one is construction minus plumbers. Okay, so this is plumber subtracted from construction. Yeah, so that's so this right here, just this right here, these values here. Okay.
That's good. So good. Negative 8.66 to 1.06. Okay, and for this one, stick with Joseph.
Can the null hypothesis be rejected or not be rejected?
Okay, cannot be, because 0 is in the interval, right?
So 0 is in this interval, plus the p-value is 0.953.
So it cannot be rejected. Okay, then the last one we'll ask Chris. Electricians minus plumbers.
Didn't we just do that one?
No, we did electrician and construction.
Oh, yeah. Okay, so now we're going to do electrician.
Will be negative 21.17 to negative 1.4.
21 point what?
Point,
It's a 1, 2, 1, 2. Okay. So everybody see that? This is what I was trying to explain before. Chris picked it up. Maybe he knew already. But here we have electrician subtracted from plumber. So we actually have plumbers minus electrician. This seems like a weird abbreviation for plumber, doesn't it? It seems like lead, right? Oh well. It should be like PLUMB. Like that character from the Clue game. Yeah. Okay, so anyways. So basically what they're giving us is plumber minus electrician, which is 1.41 to 21.12. So basically we take the negatives of those and then reverse the order to get the actual to get the electrician minus plumber. Okay?
What do we have? Negative 21.12 to negative 1.41. Is that it? Excellent. Okay, so in Chris, which one? The null hypothesis can be rejected or cannot be rejected? Can? Can or cannot?
because the p-value is small, and also it didn't go through 0.
Yeah. So it doesn't go through 0 and the p-value is small, so we reject the null hypothesis.
Nice work. And let's see, Leilani is here. Leilani's not here. How about Leona?
Yeah.
You want to read that one right there?
If there is at least one difference between means, list the group from smallest mean. On the left, the largest mean.
Okay, so smallest to largest.
What's the smallest? According to, so here, what's the smallest mean? Do you know where to look? I look right here.
It's too small.
So the means are all right here. These are the sample means right here, right? So out of those, which one's the smallest? Electrician, that's 48.5, and then next smallest? Plumber, that's 59.8, and then the largest is construction at 61. So electrician, plumber, construction. So that's, I'm gonna go with answer A.
Okay, and then the next part, Zell is going to help us with the next part. Let me push this down to the bottom though. Okay, so which ones are not significantly different? Was that electricians and construction workers? Okay, here's electricians versus construction workers. The p-value was really small.
Oh, that's right. It's the one that contains 0, right?
Yeah. So the one that the interval that contains 0, or all the intervals that contain 0, that would be
No.
plumbers and construction workers, right? And also, alternatively, you could look at the p-values. So plumbers and everything else, they seem to be significantly different, right? So we'll put a box there. That's a good job for that one. And if post hoc tests are appropriate, are not appropriate, explain why not. Well, they are appropriate, right? So we're just going to click right there. And we finished, yay. Okay. So if we want to do another exercise, we could click summer exercise. Okay, now let's take a look at number 3. I want to show you number 3. So here, random sample of people were asked whether they're athletic, moderately athletic, or not athletic, and tested for reaction speed. So that's the one where you have the ruler that you're dropping and then trying to catch it. Okay, and anyways, they came up with a p-value of 0.883 for ANOVA. So based on that, should post hoc tests be done? Or what would the conclusion be if your p-value is 0.883 for ANOVA? That means that there is not sufficient evidence, there's not significant evidence that, so the means are not significantly different, right? Okay. So, as far as post hoc tests, what should we say here? Should not be done. Okay? Because you need to establish first that they're different. If you don't establish that they're different first, then shouldn't do that. So it should not be done. And then everything becomes pretty easy here, by the way. Because blah, 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 and then you just say should not be done. Okay? Should not be done. So just keep clicking should not be done. And what I'm trying to click that. Oh, I did click it, but it didn't look like I clicked it. No, should not be done. Should not be done. And then the next part's hard. Oh no, wait, that's still not hard. That's not still not getting to the harder question. There are no significant differences, or post hoc tests should not be done. Okay, select all groups for which the sample means are not significantly different. Okay, so here's comes up with something you have to think again. And what should we check here? What's that? Check them all? Okay, just check them all, or box them all. Because they're not, none of them are significantly different from each other. So, well done. Okay, now this is where we get into other trippy. So it says, if post hoc tests are not appropriate, explain why not. This is where it's kind of like the reverse from last time. This problem's harder to answer now. Okay, so why is it? Is it because the null hypothesis cannot be rejected, or because the null hypothesis was rejected? First of all. It's because, what's that? Is it C? Was the null hypothesis rejected for the ANOVA? So at the very beginning it said ANOVA. Okay, so go back up here. Okay, so p-value of 0.883 for ANOVA, right? So if that kind of a p-value, then we don't reject the null hypothesis, right? Because it's pretty big. So we didn't reject it, and okay, now is the post hoc test to, what's the purpose of it? Is it to verify? Wait, is it to verify the null hypothesis? We correctly reject. Wait a minute. This doesn't make any sense. It says the null hypothesis cannot be rejected. Post hoc texts are used to verify that the null hypothesis was correctly. What? If it wasn't rejected in the first place, okay, that doesn't make any sense. Okay, post hoc tests are used to further investigate trends after the null hypothesis is rejected. Maybe that doesn't make any sense either. But yeah, maybe that doesn't make any sense either. Okay, but I guess they both might make some sense. This makes more sense. Because the post hoc tests are not to verify that the null hypothesis is rejected. It's to do something additional. Okay, it's to go after the conflict and try to figure out which means are significantly different. Okay? So the answer here is D. Okay, that looks like about it for the day. We don't really have time to cover anything else, so we can go ahead and have a nice weekend, and we'll see you guys on Monday. We will cover chapter 14. We'll do some more things with regression. Okay, regression and correlation.